Hi Emma,
Hello.
how are you doing today?
I'm good. How are you?
Good. I'm going to use my old drawing program today,
Okay.
which I think will work better than the new one. It
Okay.
certainly is easier to use the eraser. So, you have problems you can read?
Yeah, I do. Let's see. Okay. So I have, I might have to send you a picture of these.
Okay.
All right, hold on. Okay.
Technology is great.
Yeah.
I can't even
Uh,
imagine trying to do this 20 years ago.
I know. Alrighty, it's sent.
It's great, but it's not that great. Still time to just wait. Never instantaneous. Did you send it to David Cowan, 1949?
Yeah.
Okay. So I have another email that I use that doesn't get to me quite as quick as this one does.
Mm.
Well, while we wait for that email, is there anything you can, it just came through. My phone got it. There it is.
Perfect. Okay, so it's the piecewise ones.
Okay. Starting at 45.
Yes.
So here's what we have. We have f of x equals 3 minus x when x is less than 2, and x over 2 plus 1 when x is greater than 2. And y is c equal to 2. What are we supposed to do here? I get it now.
Mm-hmm.
So what's the limit of this exist, and if so, what it is? So if we
Yes.
want the limit of this as x approaches 2,
Mm-hmm.
that's our problem. Well, maybe it would help to graph this. When you graph it, always start right there.
Mm-hmm.
In other words, what we're looking for is a plane. Whenever x is, there's 2, so
Mm-hmm.
whenever x is in this side of that, the function is 3 minus x.
Okay.
Okay?
Mm-hmm.
Well, what is 3 minus x? That is a slope-intercept at 3 with a -1
Okay.
slope. So there's the line 3 minus x.
Okay.
And, oh, hold on, I needed to stop it right there.
Mm-hmm.
And it's x over 2 plus 1 when x is greater than 2.
Mm-hmm.
Well, to figure out where we should start, let x equal 2. When x
Okay.
equal to 2, we should be at the point 2, kind of right there.
Okay.
Right there. Because when x is equal to 2, the first function is 1. This
Right.
function is 2. And they're both open circles. And
Mm-hmm.
the slope on this function is 1/2, so it's kind of a positive 1/2, so it looks like that. And notice that at x equal to 2, this would be 1, and this
Mm-hmm.
would be 2. So that's why this circle is above the bottom circle. And there is no x equals 2, but we do have limits. So as I approach this thing from the left, what's
Mm-hmm.
my value?
So that'd be 2
As I approach
or 1.
1.
Yeah.
And when I approach it from the right, what is it?
That would be 2.
So what is it at 2?
Well, they're both open circles, right?
The key is that if the limit from the left is the same as the limit from the right, then that's what the limit is. But if they're different, then the limit does not exist.
Okay.
So that's the answer. It does not exist because from the left it's 1 and from the
Mm-hmm.
right it's 2. They have to be identical.
Okay.
Or that anything other than identical, you immediately can say it does not exist.
Okay.
Okay. Let's see. Hold on. I thought I remembered how this program worked, and I do like it better than my other one, but now something's wrong. My computer seems to be hung. Are you still there, Emma?
Yeah. Mm-hmm.
Let me try unplugging this and plugging it back in.
Okay.
Wow. Well, that was not the problem. Or was it? Well, at least I can turn it off, and now let's see if I can reload it.
Okay.
Okay, I got that far. Let's get a new note. Okay, and you sent it to me. Let me see. I'm not quite sure what happened there for a moment, but I guess I'm okay. I figured out how to get this thing working. Let's see. Let's close that note. Let's see if I snap right on that. Alright. Not quite sure what happened, but anyway, we're back to good, I think. 46 is starred. Does that mean anything?
That's just where I'm supposed to end.
Okay. So let's try that. My problem seemed to exist when I clicked on this left icon. Remember how to get, let's see if I click, there we go. I think if I click down here, I can at least scroll. So 46 is, notice it's exactly the same problem. Well, not quite exactly the same. But in other words, the top function is the same, 3 minus x. The bottom function is almost the same. It's 1/2 x, not plus 1 though. And there's a middle piecewise function that does exist at x equal precisely 2. So if, sorry, Emma, I'm going to have to open this and close it again.
Oh, that's fine.
All right. So if I draw the second one, finally, 3 minus x was to there, that being 2. That's 3 minus x. And at precisely, it's 1/2 x, but it's going to go through, let's see, when x is 2, it would be 1. So it's the same point as a slope of 1/2. Open circle right there. And then when x is equal to 2, f of x is 2. Well, 2 is up there. So I actually have a closed dot there and an open dot below it. That's my picture. And if you understand this limit problem, you won't have any problems with limits.
Okay.
As I approach 2 from the left, what is my limit?
1.
And as I approach 2 from the right, what is my limit?
Would that be 1 also?
So what is my limit at 2?
1.
Correct. Even though f of 2 happens to, in this case, be equal to 2. In other words, exactly at 2, that's what the value of the function is. But it's not what the value is at 2 that matters. It's what it's approaching, and it's approaching an f of x of 1. I make that be f of x there. As we approach 2 from the left, we're approaching a y of 1. And as we approach 2 from the right, we're approaching a y of 1.
Okay.
I'm a little upset that they used the same number here, that being 2 and that being 2. I mean, could they make it any more confusing? Could they not have said this was 4 or something? You know,
Right.
not the same number as 2.
Yeah.
The key being that at 2, it's not actually equal to 1. And that's okay. What, for a limit to exist, it merely has to be what is it as it approaches from the left and what is it as it approaches from the right.
Okay.
I have kind of a good example here of maybe a little better explanation of it. If I take the function y equal 1 over x, classic hyperbolic function, okay? Well, what's the limit of that as x approaches 0 from the left side? This is y.
Negative infinity?
Correct. What is, so let me just write, negative infinity. What is it as x approaches 0 from the right?
Positive infinity.
What's the limit at 0?
It doesn't exist.
Correct. If they are not identical, it does not exist.
Okay.
However, change the function slightly, so we have 1 over x squared,
Mhm.
and now the function looks like this. Now, when we approach 0 from the left, we have positive infinity.
Mhm.
When we approach it from the right, we have positive infinity. So you can't really say that the limit doesn't exist. It does exist. It's the same
Mhm.
from the left and the right.
Right.
Whether you want to say that that limit is infinity or not, most schools don't like using infinity as a number.
Mhm.
So they might still say that it's undefined in place of the word infinity, but this is kind of a good illustration of the difference between infinity and undefined and does not exist.
Okay.
In other words, clearly this limit exists because it's the same from the left as it is from the right.
Right.
But it's different than the 1 over x, which definitely did not exist. You cannot get two numbers further away from one another than negative infinity and positive infinity.
Right.
All right. What's the next one?
Um, let's see. Well, I have some of them for like sine and cosine.
Okay. Are they
So
still wise or?
yeah, they're piecewise.
Okay.
I probably can just read it off.
Yeah, I see like 53 are you talking about kind of?
Yeah, there's some further down too.
Okay.
Okay, so let's see. F of x is equal to let's see. So sine x, and then negative 2 pi is less than or equal to x, which is less than 0.
Okay.
And then that should be the negative 2 pi is less than or equal to.
Okay.
And then cosine x, and then 0 is less than or equal to x, which is less than or equal to 2 pi.
Okay. So on the interval from minus 2 pi to plus 2 pi,
Mm-hmm.
let's just draw it. There's minus 2 pi.
Mm-hmm.
There's plus 2 pi. So on the left side, it's equal to sine of x, which means it looks like this, kind of. Okay?
Okay. Mm-hmm.
To the right, between 0 and 2 pi, it's cosine, which looks like this.
Okay.
The key point, and let's see, is that's closed there,
Mm-hmm.
and that's closed here, or there, excuse me.
Mm-hmm.
What happens at 0? At 0 we have the right side, so
Mm-hmm.
that's closed there. And clearly they want the limit as x approaches 0.
Yeah, so it says, at what points C in the domain of F does limit x go to C, f of x exist? So,
Well, the points are from minus 2 pi to 0.
mm-hmm.
The limit exists because it's continuous.
Right.
And from 0 to 2 pi, it's continuous.
Mm-hmm.
The only place the limit does not exist is at 0. And the reason
Okay.
it doesn't exist is because the limit from the left is what?
It's a solid.
Well, it's right. What am I pointing to right there?
Oh, 0.
Right. What's the limit from the right?
That'd be 1.
Right. In other words, the cosine function begins at 1.
Okay.
And the limit from the right is the solid dot. That's an open dot. But since the limit from the left is not the same as the limit from the right, then the limit does not exist.
Okay.
It's as simple as that. That's always the ironclad test. If they are not the same, it does not exist, for starters.
Okay.
All right. What else?
Okay.
And yeah, from 0 to 2 pi, it's also continuous. So
right.
the limit at any point in there, c, is going to be the function. So there's only one point in this entire domain from minus 2 pi to plus 2 pi where there's a problem, and that's at x equals 0, or as x approaches 0. And when I say problem, I mean whenever you have a discontinuity, it's likely that the limit does not exist at that discontinuity.
Okay. Okay. So I have like 4 of the same, and they're all limit integer x.
Okay.
And then it's just like different x's approaching. So
Okay.
so one is x is approaching 0 from the right.
Okay.
And then one is x is approaching 0 from the left.
Let's do them each one at a time.
Okay.
Let's draw the greatest integer function. This is 1. That's 2. This is 1. That's 2. That's 3.
Okay.
As we approach 0, and this actually keeps going like that, but that's as much of it as we need. So as we approach 0, and remember, you're always approaching on the horizontal axis, and that's y. So as we approach 0 from the right, what are we pointing to?
0.
Correct. What's the second part?
X is approaching 0 from the left.
Okay. What are we pointing to there?
Would that still be 0?
Negative 1.
Okay, even though there's a open dot and a closed one?
Doesn't matter. It's what it's pointing to. And that's why I use that term. In other words, it doesn't really have anything to do with what it's equal to at 0.
Right.
It's what it's pointing to. If I get on my function and I go towards that point from the left, I'm pointing towards minus 1.
Okay.
So that's what the limit is as I approach 0 from the left.
Okay.
Approach it from the right, it's 0. Because as I approach from the right, I'm approaching from that point there.
Okay.
Okay, what other numbers?
As x is approaching 0.01.
What is the function equal to when you are approaching 0.01?
Would that just be 0?
Correct?
Okay. And then x is approaching 2 from the left side.
What is that?
Would that be 2?
No.
That'd be 1? Okay.
Approaching 2 from the left side. That's the only place I can approach 2 from the left side.
Right.
That's where I've drawn it. So that's 1 also.
Okay.
Regardless of the fact that the greatest integer of 2 is 2.
Right.
The fact is we're approaching from the left side.
Mm-hmm.
So all you do is just approach from the left side, and whatever number you're pointing at on the y-axis, that's going to be your answer.
Okay. Okay, so those are all the ones with that one, and then I have some with absolute value. So,
Okay.
it's the limit of x over the absolute value of x.
This is actually
And,
a piecewise function.
oh, okay.
Okay. And I say that because what is this function equal to when x is positive?
Just 1.
What's it equal to when x is negative?
-1.
Correct. So I have this function here where it's equal to +1 or -1.
Mm-hmm.
That's how I graph that function. So what is the limit of that function as I approach 0 from the left?
That would be -1.
Correct. How about 0 from the right?
Just 1.
What's the limit at 0?
It doesn't exist.
Correct.
Okay.
Were there any other parts to that?
Nope, that's it.
Okay. I found that usually drawing a graph helps enormously.
Yeah.
Just because if no other reason, you can get on the graph and you can start approaching that value from the left like that. Whatever those arrows are pointing to on the y, that's your answer. And the same
Right.
from the other direction. You can do that. Okay?
Okay.
Got time for maybe one more?
Okay. Okay, I was a little confused. There's one and it's the sine squared x over x, and then x is approaching 0.
They taught you that the limit of sine x over x as x is approaching 0 is equal to what?
1.
Okay. Well, this thing is almost that. It's sine x times sine x, that's what sine squared x is,
Okay.
over x. And now I can remove that part right there. I know that's approaching 1,
Mm-hmm.
right? So I'll put
Yes.
1 up there. Well, what is sine x as x approaches 0 going to approach?
Isn't that just 0?
Yeah, so it's going to be 1 times 0, or 0. So
Okay.
the limit is going to be 0 as x approaches 0. And
Okay.
a lot of limit problems are solved that way, where you factor one of the numerator or the denominator.
Okay.
In other words, a really good limit problem just is this one here. Limit of x squared minus 1 all over x minus 1 as x approaches 1. That's 0 over 0, right?
Right.
But after I factor it, if I factor the top, I got x minus 1 times x plus 1. Still have x minus 1 in the bottom. Now I can cancel that one with that one. So after I factor it, the function becomes that. Now what is that equal to as x goes to 1?
2.
That's the limit.
Okay.
Okay? And all difficult, the only, I should say, difficult limit problems are the ones that come out 0 over 0, which is called indeterminate.
Right.
This one started out as 0 over 0. But after I factored it, it ended up being a function where I could substitute 1 for x.
Okay.
And so all of your interesting limit problems are 0 over 0, including the one you gave me. Sine x over x, well, that's 0 over 0 as x approaches 0. So it wouldn't be exactly clear to anybody that that's 1.
Right.
But you knew it. And you can actually graph that function, and you can see that it gets close to 1, as in other words, that function looks kind of like this. And that number is 1 right there. As we get close to 0, the value of that function approaches 1. And you can certainly see it graphically when I draw it like that, although that's not proof. There is a rather complicated proof to prove that sine x over x is actually equal to 1 as x goes to 0. But this graphic illustration there suggests that it is. It's not mathematical proof of it, but
yeah.
Okay. Emma, you good to go for today?
I'm good, thank you.
Let me just look here for a moment. Okay, we're on again at 3 tomorrow.
Yes.
Talk to you then.
Okay, sounds good. Thank you.
Bye-bye.
Bye.
Figure out how to close it.